Welcome back everyone. In the previous lecture we had seen how to tune PID controllers. We saw methods like Ziegler-Nichols method for the open loop and the closed loop case. We also saw that if you know the transfer function, how you can use it to find out the tuned Kp, Ki and Kd values. Today we will look into PID controllers from an implementation perspective, in the sense that if you want to implement a PID controller, what are the problems that you will face. So here is a PD controller, the expression of a PD controller. By now you know what a PD controller is. So the controller output in case of a PD controller would look something like this: Kpe plus Kd ddt of Et, where E being the error signal. And if I draw the block diagram of the system, closed loop system, then it will look something like this. Now let us see how do we implement it in a practical setup. So in a practical setup, what will you do? So in a practical setup you will have to find out the error signal. Now how do you find out the error signal? To find out the error signal, first of all you will need a measurement here. Okay. So how will you measure that? Since you will be implementing it suppose on a processor, on a microcontroller, so you will have to sample this signal. You will sample this signal. Now when you sample this signal, you will have to choose the time period of sampling first. So suppose the time period of sampling is t. So the signal which was yt in time domain, this signal you will sample at different instance. Say for example, you will find out the value of the output at yt, you will find out the value of the output at y of t, you will find out the value of the output at y of 3t. When I say you will find out, it means that you will measure the value of the output at these instants, say. Okay, and that will feed back to the system. Now similarly, the reference signal also, you will take the reference signal. What is the reference signal? As RT at R of 2t, at R of 3t, so on. For example, suppose your reference signal was a unit step signal which looks something like this. So that means say at R of 0 the value would be, say the value here is 2. So then at R of 0 this is 2, at say R of t this is 2, at R of 2t this is 2. So this will keep on, these are the sample points that you are taking. So now with each sample you will subtract this sample from this sample after you have multiplied with it HS. Now to make our life simpler, let us again consider that this HS is 1, just to explain the thing. Okay. So suppose this is 1, then YT and RT you have. So the error signal will become E of t equal to R of t minus Y of t at the time instant capital T. In the same way it becomes E of 2t equal to R of 2t minus Y of 2t at the time instance 2t. So basically what I am trying to say here is that from the continuous domain, from the continuous time signal, we are converting these to discrete time signals during implementation. Okay. So now let us look at the controller. Now what will the controller do? So the controller will also implement it in a discrete way, because it will only get samples. It will get the first sample at t, the second sample at 2t, the third sample at 3t and so on. So in that case the controller, the discrete time implementation of the controller would look something like this. So at different values of k, at k equal to 0, at k equal to 1, at k equal to 2, you will have this expression where this part is getting replaced by Kp into E of Kt okay, and this part, that is KD, the differentiation part here of the continuous signal ET in the discrete domain will look something like this, right. This is from the definition of differentiation. So, what will be the numerator here? So, the future error E k plus 1 t minus E of k t divided by k plus 1 whole t minus k t. This can also be written down in this form, where I am dropping the t and I am writing the equation in terms of a discrete time difference equation. Now, notice this. Now, suppose I want to implement this. What is the problem in this expression? Think about it. Look at the expression and you see that here, if I have to find out the input ut at the kth instant, say, it depends upon the error at the k plus 1th instant, and that is an issue. So, this becomes a non-causal system now, and we know that implementing a non-causal system is a problem, right. For a physical system, physical realizability is an issue. So, this cannot be implemented directly like this. Okay. I can show you that using Simulink as well. Notice in this Simulink model, what I am doing is I am taking Gs to be a transfer function 1 by s square plus 3s plus 2, and then I am trying to implement this PD controller here. So, I have the error block, and with the error block I will try to implement these two blocks. Notice that these are just Kp and Kd are just numbers. So, these are gains. So, that is why I am taking two gain blocks, one of them will be Kp and the other will be Kd, okay, and that is what is being done here. So, I am connecting those two gains, and now I will try to put this. This is nothing but differentiation in the time domain. So, I will try to put a transfer function there. Now, what will be the transfer function of this? What is the transfer function? What is the numerator? The numerator is 1 0, and what is the denominator? The denominator is 1, the coefficient. So, this is s by 1, right. The coefficient is 1 0, numerator 1 0, and the denominator is 1. And once I do that, you notice that I am getting an error. What it says is that a time domain realization of the given transfer function for block failed. Check values of numerator and denominator. What is the cause? The cause is that the given transfer function is an improper transfer function. S by 1 is an improper transfer function, because the degree of the numerator is more than the degree of the denominator. So, the order of the transfer function numerator must be less than or equal to the order of the denominator for it to be realizable, and that is why we are not able to write down the or we are not able to write down the transfer function, we are not able to implement the transfer function in Simulink. Okay. So, what can be a way out for this? Okay. Now, a simple way out is, this is what is generally done, is that instead of taking this to be the difference equation corresponding to the derivative action, we take this to be the difference equation. Okay. Now, in this case also we are finding the difference between two samples of error, consecutive samples of error divided by t, but in this case the consecutive samples, you see in this case the present sample and the past sample, we are finding the difference between the present sample and the past sample, not the future sample and the present sample. So, that is why this implementation becomes implementable. Okay. So, in this case you will see how do I take care of this. Now, how do I ensure that this has been implemented? So, in Simulink what can be done is that, so in place of the transfer function I can use what is known as a derivative block. Okay. So, it computes the approximate continuous derivative of a continuous function, this block. Okay. Using this block you can implement the derivative part of the controller. Okay. You see in Simulink there is a direct module, direct block by which you can implement a PID controller, but I am not showing you that. I mean, I just want to show you how to implement the PD controller in general. So, now you see you will be able to implement this controller directly. So, we are giving a step input as the reference. So, here is the step input as the reference, and then finally a scope as the output. So, you can see the output will be shown here. So, this is the output of the system. Now, if you change the gain, of course, the response will change. I am changing the Kp value and you can see the response has changed. Okay, you know how to change the Kp and Kd values, what are their effect, you know already. So, in this example, the main idea is not that, the idea is that this differentiation that is there has to be implemented such that we find out the difference between the present error and the past error, and then only you can implement it. One more important thing here is that while implementing, some people also do this. Basically what they do is they implement this instead of, so this term here, is also a constant, right? So, they call it say Kd, some number Kd dash. So now this becomes Kd dash. So, instead of finding out Kd, they find out Kd dash, because Kd and Kd dash are related by T. So, implementing this is easy now. Basically what you have to do is you have to find out the error and then you have to find out the difference, multiply it with Kd dash, and the error you multiply with Kp, add them up and they will give you the control action for the PD controller. Fine, this is implementation, okay, but there are some issues with PD controller as well. So, what are the issues with PD controller? Now, the issue with PD controller is noise, okay. Let us look at the issue with PD controller. We have the same setup, the only thing now is that suppose in the input somehow some noise is getting in, which can happen always. When you are using sensors will always have some noise that will be there, okay, that noise will always corrupt the actual signal. Now, let us think of that noise as a additive noise. Basically the actual signal here is HSYS, okay, but plus with that some noise is coming in. So, this noise I am taking it out separately as n of t, okay, in time domain n of t, in Laplace domain n of s. Now, look at this and think about this system. Let us think about this system. Now, this part we have already talked about. This is the PD controller, theoretical PD controller that is implemented. Now, if there is noise, then what will happen? This noise will also go in and that will result in this extra term of Kd and K by T. Okay. Of course, Kp, there will be another term of Kp and K as well, but I am just focusing on this because this is just a multiplication with the noise. I am more focused on this, okay, because this will introduce lot of problems. Now, when you have Kd and K by T, notice if your Kd value is too high, then Kd by T will be a number which will amplify your noise. In this case, Kp is multiplied with Nk, but in this case Kd is also multiplying with Nk. So, but the point is that in a PD controller, if you have noise coming in, then this derivative part will amplify the noise, which means the output here will have an amplified version of the noise that will add to the output of the controller, which is a problem for the system. So, for example, let me take an example, okay. Suppose Kd is 1, okay, and T is say 1 millisecond. So, T becomes 10 to the power of minus 3 seconds, right. Then Kd by T, notice that becomes 10 to the power of 3. So, which is a big number, because the sampling times are generally will be less than 1 second. You won't generally wait for 1 second for a new sample. These are in milliseconds generally. So, which means that this Kd by T term will be a very big number, okay. So, that is the problem. So, that is why you try to keep the value of Kd as small as possible. There is another issue. Look at the other issue is that suppose the reference signal, if you have let us talk about the drone itself. The drone, suppose you wanted it to fly to a particular altitude, say 1 meter, and then after some time you change the 1 meter altitude to say 10 meters. You have made a big jump in the reference. So, which means the reference will look something like this. It will go up to say 1 meter, and then after some time you are making it 10 meters. So, this is the reference. So, this is 10 meter and this is 1 meter. Okay. So, you can see that there is a jump. Now, as soon as there is a jump, what will happen at this point? At this point, since that there is a jump, there will be a big difference in the error. So, the error signal will be very big. Now, if the error signal is very big, when you differentiate, so suppose you differentiate at this point, what will happen? If you differentiate a step signal at the point where there is a rise, where there is a change, there will be a discontinuity, right? If ddt, if you do a differentiation there, okay, and those are the points where there will be big spikes at the output, okay, which might actually damage the system, because the system GS might not be able to handle these big jumps. Okay. So, what I am trying to say is that when you use a PD controller, there is a problem with noise and sudden change in reference, okay, and that needs to be taken care of, and that is one of the reasons why the value of D is not generally very high. Whenever you use the value of D, generally it is kept very small, so that it does not affect the noise too much. Okay. We have an issue. How do we solve this problem? Now, to solve this problem, what is generally done is that a filter is used. Okay, a filter of the form A by S plus A is used. Now, what kind of a filter is this? If you find out the Bode plot of A by S plus A, you know what Bode plot is now. If you find out the Bode plot of S plus A by S plus A, approximate Bode plot will look something like this. A will be your corner frequency, and at the corner frequency you will have a minus 20 dB per decade slope, okay, and it will initially be a 0 dB line. Now, look at this Bode plot. It means that at lower frequencies the output will not get affected, but at higher frequencies the output of this block, at higher frequencies the output of this block will get attenuated. Okay. If you look at the Bode plot, that is what it means, because these are points. What are these points? These are the magnitude of the output, right, and you can see the magnitude of the output decreases as the frequency increases. Okay. So, by magnitude of the output, as I mean magnitude of the transfer function, okay, and then this magnitude of the transfer function will affect the input that is coming in, right. So, at higher frequencies the magnitude of the transfer function is very small, okay, which means that this small number will multiply with the magnitude of the input that will come in, and the input will also get attenuated. So, that is why these type of systems are also called low pass filters, because it allows lower frequencies to pass through without attenuation, and it highly attenuates the higher frequencies. Now, how does it help us? It helps us because noise is in general a high frequency signal. Okay. Now, if noise is a high frequency signal, when it will pass through a low pass filter, noise will get filtered out. Okay. And that is the reason we go for this type of a setup. This is a solution. So, when you implement a PD controller, you do not just implement a PD controller where there is a D part and a P part. You also add a filter, low pass filter with the derivative part of the PD controller, so that you keep a check on the noise in the system. Let us look at the implementation problems of a PI controller. Okay. First of all, let us try to understand how will you implement a PI controller. For a PD controller, you went for the difference method, right. Now, how do we implement a PI controller? Now, to implement a PI controller, again by the same logic that we have used, sampling the output, sampling the reference signal, with that basically the controller output for a PI controller in this form, in the continuous setup, can be written in the discrete time implementation as this, because integration is nothing but addition of each of the samples of the error. So, you see here this part is taking care of the integration. Okay. So, this is how we implement a PI controller. Now the comes what are the problems of a PI controller. So PI controller implementation is also again easy, right? There is no problem of non-causality in this case like that of the PD controller. But in case of a PI controller, there are some other issues. Okay, what are the issues? Now suppose that the set point rises suddenly. Okay, so again same problem like the D part. So suppose there is a sudden change in the set point, then there will be a large error, right? There will be a large error, and since PI controller is summation of the errors, large error means that the output in this case will also be large, right? Suppose that at E of 7 you were at 1, and at E of 10, E of 8, this next sample itself the error becomes say 100. So then what will happen? This will be, this summation will be mostly dominated by this 100 term, right? So then the error value increases here, and as soon as the error value increases here, the UK or the output of the controller also will increase. Okay. Now how is it a problem? Now this is a problem because suppose for example the plant that you had is a drone, say. Okay. Now drone means the motors will be the ones which are your main actuators here, right? Now if you have the motor, the motors will have some limit on its input because they have some rated voltage, right? You cannot give more than the rated voltage because it is at that rated voltage that it will run on the rated RPM of the motor, right? Now suppose the output of the controller because of this change in the set point becomes very high, okay, and the output of the controller is more than the rated voltage, then what will happen? Will the plant be able to respond to that? No, right? Because think about it. So suppose the motor of the drone was operating at 12 volt 100 RPM. Beyond this it won't work. Okay, suppose the motor was at 10 volt 100 RPM and the output here is say 11 volt. Even if you give 11 volt to the system, one thing might happen is that the motor might burn out. Okay, that is one case. The other case can be that the system is such that after 10 volt the motor does not even respond to whatever input you are giving. In that case what will happen? The motor will be stuck at 100 RPM because 10 volt was giving it 100 RPM. After 10 volt whatever if you give doesn't matter because it will always be, the maximum speed will always be 100 RPM. Now if the maximum speed is 100 RPM and suppose you are desiring 120 RPM, suppose your desired is 120 RPM, okay, and the output here is stuck at 10 volt, it cannot go beyond that. So the RPM is stuck at 100 RPM. Now what will happen if it is stuck at 100 RPM? If it is stuck at 100 RPM, the error will always be 20 RPM here. Okay. Now for the P controller there is no problem. Kp will multiply with 20 and give you something. Again I am considering this to be 1. Okay. Now think about the I part. The I part adds all the errors of the previous instance. So at suppose at k equal to 8 you had an error of 20 RPM. At k equal to 9 also you will have an error of 20 RPM. At k equal to 10 also you will have an error of 20 RPM because the output here cannot go beyond 100 RPM. Whereas the reference that you have given is more than the rated value. So there will be an accumulation of the error. So every time instant 20 plus 20 plus 20, the integrator will keep on accumulating error, and this is what is known as the wind up problem. So the error keeps on accumulating here. Okay, now there is no way that you can get rid of this error, right? So then what will happen? I mean, anyways you are not able to reach to the correct point. So somehow you have to bring down the error or the output of the controller will keep on growing. Okay, this is one problem. The other problem is suppose you gave 120 RPM and the motor cannot go beyond 100 RPM, and after some time you realize that okay I need to bring back the RPM. So instead of 120 RPM now you have changed your reference from 120 to say suppose 70. Okay, now what will happen? Now the speed, the output is 100 RPM, output as in output of the motor, the speed of the motor is 100 RPM. If the speed of the motor is 100 RPM and you have given a reference of 70 RPM, then what will happen? then the error, now you see we have, so we will have 70 minus 100 which becomes minus 30. So, we have a negative error. So, then gradually the RPM will come down, but since you had already accumulated so much of error, to bring it down to 0 will take lot of time. This is called winding up. You will have to wind up the error that has been accumulated. Okay. This is a problem in PI controllers, and this also can be tackled just by writing a few lines of codes actually. Okay, and that is what we are going to look at in the demo next. Now we look into the wind up problem that PI controllers face. The setup is the speed control of a DC motor. We are using a PI controller here. The hardware implementation is exactly similar to what we had done for the Ziegler-Nichols demonstration. So the code is getting compiled and uploaded to the Arduino board. Here is our MATLAB script. Now in the MATLAB script you can see that we have kept only the PI controller KP.4, KI.3, and important point here is that we have two set points here. The first set point is 35 and the second set point is 15. So initially we are giving a reference of 35 RPM. We want our motor to run at 35 RPM. However, the motor that we are using has a limit of somewhere around 21 RPM. So, of course, the set point here is more than what the motor can do. So, here is where we will face the wind up issue. After 10 seconds, say we realize that the reference is too high, and then we bring it down to 15 RPM. Now, let us see how does it affect the outputs. So, here let me pause the video a bit and explain the plots once. Here, this top part plot, here the dashed red line is the reference. So we are initially giving 35 RPM, and then at 10 seconds we are changing the reference to 15 RPM. Okay. The blue line here is the measured output or measured RPM of the motor being the DC motor that you can see in the picture. Then on the bottom plot, we have two plots again. One is this line, dotted line. This dotted line is the V max. Basically, this is the maximum voltage that the DC motor can be given. This is the rated voltage. So, at this rated voltage, the DC motor will always run at the rated RPM. Okay, it cannot go beyond that. Now here, or it should not go beyond that, we should avoid going beyond that. Here you will again see two plots. One is a brown colored plot, which is basically the output of the integral. Okay, so you have a PI block here. So P will have an output, I part will have an output. Both of them gets added up to give you the output of the controller. We are plotting the output of the integral part only using the brown colored plot, and the output of the controller is being shown using the pink color plot, which we are calling as U raw. So that is the output of the controller. Okay, so now notice that we have kept the RPM, desired RPM, to be much higher than what the rated RPM is. The rated RPM is somewhere around 21, 22. Okay, so let's see what happens. And you can see, as soon as I start this, you can see that the output of the motor cannot go beyond the rated RPM. So the rated RPM was somewhere around 21, 22, and you can see that the actual measured output here is never above that rated RPM. Now let us look at the output of the controller. So you can see that since there is always a error, right? 35 was our reference, and the output that we are getting is lower than 35. So there is always an error. This error will get accumulated by the integrator, because the integrator is summing up the previous errors, and you can see that the output of the integrator keeps on increasing. The brown colored plot, you can see it keeps on increasing because of that. Now since the I part of the controller is increasing, the output of the I part is increasing, so when it adds up with the P part, the output, the actual output of the controller also will keep on increasing, right? And that is what you are seeing in this pink plot. However, remember, although the output of the controller is increasing, this output of the controller goes to the DC motor, right? So if, although the output of the controller is increasing and it is above the rated voltage, even then the output of the motor here is not increasing, okay, because the motor cannot go beyond 22 rpm. Okay, so let's keep on doing this. Now at this point you have realized that okay, reference signal that we gave was higher than what is the rated rpm, so I brought the reference signal to 15 rpm. Now what is happening, now the measured rpm is 22, whereas the reference is 15, so therefore 15 minus 22, there is a negative error, and which means when we do integration, now the error terms are coming down, because the previous error will now be, we will subtract from the previous error the new error that we are getting instead of adding, because there is a negative sign coming in the error. Okay, and you will see that the integral output, the output of the integral controller will come down now, and as soon as the output of the integral controller comes down, the combined output of the PI controller also should come down, which is basically the pink colored plot. You see it is coming down now. Okay, notice still the error, still the measured rpm has not decreased. Why? Because still the u raw, which is basically the output of the controller, is higher than the maximum input that you can give to the DC motor. Okay, so now you can see that the output of the controller, the pink plot, is coming down, and as soon as it will hit the Vmax line, which is this dashed red line, that is the point after which the motor will start reacting, because once it reaches Vmax and goes down below Vmax, the speed of the motor will decrease. But when the output of the controller is more than Vmax, the speed of the motor remains at 22 rpm or the rated voltage. And you'll see that we will hit that spot soon. So at this point, t equal to 25 seconds, you can see that we have hit the Vmax line, which means now if you see the error is still coming down, because error is negative still, right, because the measured output is still more than the desired output. The reference is 15 now, so the output of the integral will keep on decreasing, and which means the u will also decrease further. That means it will go down below the Vmax, and you will see it has gone down below Vmax, and then finally you see it has reached your 15 rpm. So this basically shows the issue. You see, the issue was that it has to wind up this amount of accumulated error. It accumulated so much of error that to wind it up, it took almost 25 minus 10, almost 15 seconds to wind up the error, right? So this is the wind up problem. So now to handle this problem, what we are going to do is we are going to limit the output of the integral controller. So we say that if the integral controller is output is say above 50, we will stop the integral controller, because you see what was the problem? The problem was that if the error keeps on accumulating, okay, then the integral's output keeps on increasing, and if the integral's output keeps on increasing, then the output of the controller as a whole keeps on increasing. However, after reaching a threshold, if we stop the integral, then this output will not increase. So that's what we are going to do now. So you see, for example, you see if you look at the brown plot, which is the output of the integral, as soon as it hit, say suppose approximately 51, 52 here, we have stopped the output. So basically now the output remains saturated at whatever value it has reached. So there will be no increase now. The output of the eye controller becomes a constant. Now what will happen is, you can see that if I keep on going at this point, okay, now what will happen at this point, at 10 seconds the set point has decreased. Now you have see there has been no build up of error as such. There has been a little build up, not much, okay, which can easily be reached. You see now within only 2 seconds I could wind up the entire error. Okay, now what should be your threshold? That you can take a call. That is up to you. Okay, how much you can tolerate, that you can always take a call. Okay, but this is how we can actually get rid of the wind up problem. Okay, and this is just a simple if statement, that okay, if the output of the integral is more than this amount, then you have to stop it. So it is just a simple line of code in Arduino. Okay, and this is how we can take care of the wind up issue that PI controller faces. Now that we have looked into the demo of implementation of PID controllers, you would realize that this is not such a big thing, right? Once you understand what it is a very simple implementation. You just have to sample the errors or sample the output, find out the errors, and then write down the equations of the PID block. Depending on what you need I, you need D, you need P, you just have to implement them. Thank you.